Okay, here we go. All right, so last time we started looking at systems of linear equations. So what's a system of linear equations? It's a bunch of linear equations. We want to solve such a system, which means finding all possible values for the variables that will satisfy every single equation in the system. We then introduced a notation for our systems of matrix representations. I've shown you one with the coefficient matrix and the constant matrix and the matrix of variables, and which can be used to solve systems when the matrix of coefficients is invertible. Since we know only of how to compute the inverse of a 2x2 matrix, we're not going to go in that direction. We're going to look at Gaussian elimination. So we've introduced a second notation for our systems, which is the augmented matrix, where you have the coefficients and the column of constants all in one matrix. Okay. So again, I remind you of the overall strategy. The strategy is to transform our system into a triangular system, and then use back substitution to solve the triangular system. So here's a slide which was our last example of solving a triangular system. So notice that the matrix, sorry, but we're not looking at the matrix, which is the system here, where the coefficients of the variables below the diagonal are all 0. And then the system becomes very easy to solve this way, where you start at the bottom and you have a single variable where you can just simply solve immediately. Once you have the value for that variable, you go up one equation, which has two variables. Since you know the value of one of them, you can plug in, solve for the other, and you keep doing that. So you go to the equation just before, you have the value of two of the variables, you can find the third, and so on and so forth. Okay, so once you have a system in this form, by back substitution, it's pretty straightforward to solve. Okay, so now today our goal is to see how we can transform a system into triangular form. Okay, so that'll be the theme of today's lecture. Okay, so again, I've gone through these slides briefly last time. Let's do it again. So what we want is to transform our system into a triangular system, and obviously we want both systems to have the same solutions, right? Otherwise this makes no sense. So we want to make sure that the transformations we are making preserve the solutions. Okay, so what we're going to do is to play with the augmented matrix, and there are moves that we can use on this matrix. They are legit. We are okay using them because we will see that they do not change the set of solutions. Okay, these are called elementary row operations. These are operations on the rows of the augmented matrix. Okay, and Gaussian elimination is applying these elementary row operations in a certain order to go from our original system to a triangular system. That's basically what it is. Okay, and hence the name elimination. We're eliminating variables in the description of the system, right? So that's the idea. Okay, so let's take a look at, yes. Okay, so let's take a look at these elementary row operations. There are three kinds of them. Here's the first kind, which is the simplest one of all, which is exchanging two rows. So what I've drawn here, what I've pictured here is a matrix, which would be our augmented matrix, let's say, and the resulting matrix on the right. Okay, so I just exchanged two rows. I flipped two rows, rows 1 and 2, right? So I go from the first matrix to the second matrix, I flip two rows. So that's one kind of elementary row operations, exchanging two rows. Okay. Second kind of elementary row operation is multiplying a row by a non-zero number. So here's, in this example, you can see that I've multiplied the first row by 2, right? So if you multiply every entry of the first row, 2 minus 3, 1, you get 4 minus 6, 2. Okay, so this is the second kind of elementary row operation. So we can always use these, and I'll spend a few minutes after just trying to convince you that it doesn't change the set of solutions. The last one is sort of the more involved one, is adding a multiple of a row to another row. Okay, so let's see what this is. So here I start with the matrix on the left hand side here, and what I'm doing is I'm adding to row 2 twice row 1. Okay, so what does that mean? You see that row 1 does not change. Okay, it does not change, but what I do is I add twice this row to the second one. So what does it mean? 2 times 2 is 4 plus 3, that gives me 7. Then twice minus 3 is minus 6 plus 3, that's minus 3. Twice 1, that's 2 plus 9, 11. Okay, so I've added to the second row, to the second row here, I've added 2 times the first row. So that's the resulting matrix on the right here. Okay, so only the second row has changed. Okay. Okay, so these are the three types of elementary row operations. Okay. Okay, so what's super important is that these operations do not change the solutions of the system. Okay, so what I'm going to do is to try to convince you of this. So for the first one, so you have to think in terms of the original system of equations. Okay, so if I'm exchanging two rows, what am I doing to the system? I'm just writing my equations in a different order. I hope this is obvious to all of you that this will not change the solution. This is obvious, right? I'm just not writing the equations in the same order. It doesn't change the solutions, right? So clearly I can always do that, and I'm not going to change the solutions, right? Second one, this is a property that you know, right? If you have an equality and you multiply both sides by a non-zero number, you're not going to change the truth of that equality. It's the same, right? You're not going to affect that. So x equals to 5 or 2x equals to 10, these mean exactly the same thing, right? They do not change the solutions of that equation and hence of the whole system. So certainly I'm allowed to do that. I can multiply a row by a non-zero number. The last one is the only one which is not so obvious. Okay, so the simplest way I can say it is by saying this. So you're playing with two equations, right? So suppose the first one is A equals to B and the second one is C equals to D, right? And I'm adding a multiple of the first equation to the second one. So suppose I'm adding K times A to C and K times B to D. Since A is equal to B and C equals to D, for sure, KA plus C will be equal to KB plus D, okay? Now, conversely, if KA plus C equals KB plus D, I could subtract if A is equal to B, right? So K is equal to KB, I can remove that and I'm left with C equals to D. Sorry, this is a bit I mean, without writing it on the board. But if you think about it, you see that if you think of A equals to B and C equals to D as your two original equations, right? Then in the next matrix, you'll have A equals to B and K plus C equals KB plus D. You're not going to change I mean, this is still true, and it's true both ways, okay? So these kinds of operations will not change the set of solutions, okay? Again, this one is not as immediate as the other two, but if you spend a few minutes thinking about it, you should be able to convince yourself that you can do this without changing the set of solutions, okay? So hopefully you'll believe this, that these three moves that we can make, types of moves, because for each there are many ways that we can use them, but these types of moves on the matrix are not going to change the set of solutions. So in theory, what we could do is, starting from any augmented matrix, we can play these moves as many times as we wish, in any order we wish, and the resulting matrix will be the augmented matrix of a system that has exactly the same solutions, okay? So the question now is in which order do we apply these rules? So of course you could just apply these and mess around, and unfortunately, if you don't pay attention to what I'm saying or practice it, that's what you'll end up doing. And I've seen it, where everybody figures out, okay, yeah, I'm allowed to do this, I'm going to try this, and you start messing around, but you can go in circles. And so, but there's a simple, precise way to apply these operations to get to the triangular system. So here's how it goes, okay? So what you want to do, the first step, so this is an algorithm, this is really a very simple program, if you wish. You start with an augmented matrix and you apply these rules as follows, okay? And there's a recursive part, okay? So let's start at the beginning. What you want first is to have the top left entry of your matrix to be non-zero. So how do you do that? Well, just hello. Yes. You exchange rows until you have that, okay? So think about it, there has to be at least one non-zero entry in that first column. If not, then that variable is not used. So that's silly. So for sure you have the first column, there must be a non-zero entry. So you can swap rows until you get a non-zero entry top left, okay? I'm gonna do an example after here, okay? So I just wanted to write down the procedure so you have it, but I'm gonna do an example after. Okay. Second is, now that you have a non-zero entry in that top left corner, you'd like to make it 1. So how do you do that? With an elementary row operation, multiply that row by the appropriate scalar and you can make it 1, okay? So basically you divide by that number, but you're multiplying by 1 over that number, okay? So now you've got a 1 in that top left corner, okay? And what you want, and that's the key point now, is to make all the entries below this non-zero entry, which is now a 1, you want to make them 0. And then that's the third kind of row operation that will allow you to do this, where you're going to add to these rows the correct multiple of the first row, okay? So now you'll have made the first column 1 and all zeros below it, okay? And now after that, what do? You just repeat exactly the same procedure, but forgetting the first column. And then it's recursive and you just repeat and repeat. Eventually you'll get what you want, okay? So that's the algorithm. It's very simple, right? You see, that's just basically three steps and you repeat, okay? So I'm going to show you a full example, top to bottom. So how you use that, how it works, the Gaussian elimination, and hopefully this will be good for you. Okay. So here's the system we want to solve. So we have 3 variables and 3 equations. I'd like to solve this system. So the first thing I'm going to do to make my life much easier is just to write down the augmented matrix. You see, lots of, I mean, there's, if you think about it, once you know that columns correspond to variables and the last right-hand column corresponds to those constants, you don't need to write down those equalities and variable names, right? The crucial information is all encoded in that matrix. Okay, so first step of the algorithm is to make the top left entry non-zero. Here, what do we need to do? Nothing. It's already non-zero. Okay, so I don't need to exchange rows to make that entry 0. Next step would be to make that entry equal to 1 by multiplying that row by the correct scalar. I don't need to do it. It's already 1, so I'm very happy with that. Okay. So I'll show you a non-trivial case right after, you'll see. Okay, so finally, what do I want to do? I want to make those 2 entries, this entry and this entry, I want to make them 0. In other words, I want to apply some row operations that will create a new matrix where these entries will be 0. Okay, so how do I do that? Okay, I'm going to multiply, I'm going to add to these rows an appropriate multiple of the first row. Okay, so let's do that. Here we go. So that's our augmented matrix. And I want, so let's take a look at this row. Okay, so it starts with a 2. I want to make that 0 by adding something to it. So I want to add -2 to it, right? Using the first row. So I'm going to do -2 times the first row plus the second row, right? So that's exactly what I do. Okay, so it's -2. So this is one of my elementary operations, multiple of a row added to another row. Okay, so -2 times the first row, and I add that to the second row. So -2 plus 2 is 0. 6 minus 4 is 2. -4 plus 2 is 6. -12 plus 18 is 6. Okay, so that's what I get here. This is the only row that has been changed, right? It's this one. So this is -2 times the first row plus the second row. This is the resulting row 2. The first and the third did not change. Okay, so that's done. I want to do exactly now the same for the last row. I've got a -3 here. So I want to do 3 times the first row plus this one. That'll give me what I want. So 3 times the first row plus the first row plus the third. Here's what I get. So 3 times 1 minus 3 is 0. 3 times -3 is -9 plus 8 gives you -1. Then -6 plus 9 is 3. And 18 minus 9 is 9. So this is my new row 3. Okay. And again, all I've done is used elementary row operations. That's all I'm allowed to use. Okay. All right. So now look at this new matrix. So we know that row operations, these elementary row operations, do not change the set of solutions. So I'm looking for the set of solutions of this original system. This one I know has the same solutions. But look now that in the second and third equations, I've gotten rid of a variable, right? So I want to go to that triangular form, and I've got the job done here. So there's only one last step to do, basically. I mean, this is a small example, right? Okay, so let's go to the recursive part. So now what I want to do is repeat exactly the same procedure, but I forget about the first row, first column. Okay, now what I mean by forget about them, I don't mean don't write them, right? We usually, the standard way to do this is just you rewrite the whole matrix, you keep it there, but you don't touch those, okay? So this is the augmented matrix that we have at this point. Now I don't consider the first row, first column, okay? So let's just outline those. Okay, so now what I want to do is just consider the smaller matrix in a sense. So now when I talk about the first column, I mean this column here. Okay, so I'm going to repeat the procedure with this column here. Okay, so that's what I'm saying here. Okay, so the first entry of row 2, this guy here is non-zero, so I don't need to swap rows. Okay, I don't need to do that. Notice again here, if you had a 0 and you're going to swap rows, you do not use row 1 ever. You don't touch it anymore, because if you start doing that, you will screw up everything you've done. You do not touch row 1 ever again. Okay, so here it's non-zero, so I don't need to swap rows. Okay, it is not 1 though, so I want to multiply that row by the correct scalar, which is 1/2. Okay, so I multiply this row by 1/2. This is what I get, right? So 0,266 becomes 0,133. Okay, and now I'm ready to implement the third part of the procedure, which is make all the entries below this 1, which is called a pivot, but you don't need to know that. We're going to make those 0. Okay, and here we're like super happy because it's like, it's really easy, right? 1 plus minus 1 is 0. All I have to do is add row 2 to row 3 and I'm fine, right? So let's just go to the next slide. Okay, so all I have to do is add row 2 to row 3. Okay, so again, you see row 1 does not change, row 2 does not change, it's done, and I add row 2 to row 3, 0, 6, 12. That's my last row. Now look at this matrix, it has the form we want. Okay, now there's one last operation that you can do if you wish. So you see the last row, 0, 0, 6, 12. It's very tempting to multiply it by 1/6. You can do that. That's obviously you can do that, right? So now, because it's a legit elementary row operation, and obviously is going to help us in our back substitution. So why not? Might as well do it. Okay. So this is the augmented matrix of a system, and we know by the way we obtained it that it has the solutions that we're looking for. It's the same as the original system. Okay, so this is the augmented matrix we've obtained, and what is the associated system? It is this, right? So x minus 3y minus 2z equals to 6, y plus 3z equals to 3, and z equals to 2. So now back substitution, you don't even, I mean, when you do a lot of these, at some point you realize you don't even have to write the system. You can just use the matrix. It's the same thing, right? But let's just use back substitution to solve this one. And that's easy. Z equals to 2. And then you substitute z equals to 2 here to find y, which will be minus 3. And then you substitute y and z in this one, you'll find x, which is 1. And that's it. Okay. Now, if you had, let's say, 4 equations, 4 unknowns, it's the same thing. You'll just have one extra loop in your recursive procedure to do it, but it's exactly the same thing. Okay. And it's 5, 6, 12, 15. They're all the same. It's always the same. It's a very, very simple procedure. Okay. So that's Gaussian elimination. Okay. So now I didn't do I mean, this example, so okay, let's go back briefly. Um, we've talked about this last time where systems in general can have, there are three situations. There's the situation where you can have a single unique solution. There is the possibility of no solution, and then there's the possibility of infinitely many solutions. The case of infinitely many solutions, you might see one or two exercises that deal with it, but I'm not going to test you on that because it takes us somewhere else. We don't want to go there now. Okay. So the systems that you are going to see are either like the one I just did, unique solution, or no solution. Okay. So let's just take a look at this. I'm going to switch to the iPad. Hopefully it is charged up. Not bad. Okay. No, don't do that. Okay, let's do that. Let us share something else. All right, so systems can have 0 solutions, 1 solution, well, that's, or infinitely many. Okay, but this one I'll just put like that because we're not going to see those. Okay, so basically you can expect your systems to have no solutions or 1 solution. Okay, now let's try to think about this. How can you have a system of linear equations that has no solutions? How would that work? Let's try to cook up a system that has no solutions whatsoever. Let's try that. Okay, let's see. 2x plus y equals to 3. That'll be my first equation. And now I'd like to add an equation that will make it, will make this system have no solutions. Well, here's an easy way to do it. 2x plus y equals to 5, right? Hopefully you see that there are no solutions to this system, because if you plug in values for x and y such that 2x plus y is equal to 3, it'll never be equal to 5, since 3 is not equal to 5, right? So this one has no solutions, right? That is clear. Okay, so what happens if you apply Gaussian elimination to this? You know what? I'm gonna cheat. I'm gonna change the system because I don't want to get into fractions. Let me just make it a little different. It's a x plus 2y, x plus 2y. Okay, so let's see what happens if you're trying Gaussian elimination on this. So the system augmented matrix is 1, 2, 3, 1, 2, 5. This is the augmented matrix, right? Okay, so now let's see what happens like that. Okay, so let's apply Gaussian elimination. Let's just see what happens. Okay, so first step, I want to make this entry here top left non-zero by flipping rows if necessary. It's there, it's fine. Then I want to multiply that row by the correct scalar to get a 1. I got a 1, I'm happy. Okay, and then I make what's below it 0. So how do I make that 0 here? I'll do -1 times row 1, and I'm going to add that to row 2. Okay? So what do I get? I get this. So the first row doesn't change. 1, 2, 3. So minus 1 plus 1 is 0. Minus 2 plus 2 is 0. Minus 3 plus 5 is 2. And do you see what happens, right? You're going to get, so this has the same solutions, right? And this is the augmented matrix of the following system. Let's write it up. X plus 2y equals to 3. And this is 0x plus 0y equals to 2. Now, clearly, this has no solutions, right? The second equation is just 0 equals to 2. Obviously, has no solutions, right? So this is the situation where you should be looking for when you're doing. I mean, I've used a 2 by 2. It could be a 5 by 5, but basically the last row, once you've done the whole Gaussian elimination, it's the last row that'll tell you if there's a solution or not. Okay. And in fact, it would be also the case for infinitely many solutions. If you can figure out what the last row would be for infinitely many solutions, you can think about it. But again, it's beyond the scope of this course. But so this is the telltale shape of that last row, right? Where you have all zeros except the last entry, which is non-zero, then clearly you have no solution. Okay, so all zeros, not zero. So this is true in general for any number of variables and equations, right? So if you have something like that, then you have no solutions. And otherwise you'll have, I'm just curious, can anybody see what it would look like, that last row, to get infinitely many solutions?
Maybe if the last row is all zeros.
Yes, exactly. If it's all zeros, you're going to get more than one solution. You're going to get infinitely many solutions. Yeah. So this way, what happens is that when you go to the previous row, let's say, then you'll have you get what we call free variables. So you can just plug in the value you want for, in when we get this unique solution, that last variable is we get a single value, which forces a single value for the previous one, and up and up and up. But if that last row is all zeros, then suddenly you get a free variable. You can give it whatever value you want, and by giving it any value you want, then you can give corresponding values to the other variables. So that's what's going to happen. Yes, very good. Okay. All right, so this is the end of the material. Okay, so in theory, there's a little last piece that I should be doing, but because of the state of the world, we're not gonna do it. Okay, I mean that's it. I'm gonna stop here. Okay, because I think I didn't get that much feedback from you guys personally, a little bit, but the feedback I get overall is that everybody's going like this. So I suspect it's the same for you. So this is it. On Monday, I will do problems for chapter 3, and on Thursday is our last test. That'll be it. Okay. Are there questions, comments at this point?
Did you have posted all the web work? Or are they gonna have more?
No, that's it. They're all there. They're all up there.
Oh, okay,
Yeah.
good.
This is the end of WebWorks. Yes. I mean, you still have some to do, but no, it's what you see is what you get. Yeah.
Okay, good.
Yeah. Okay, all right. I'll just stop the recording.